Okay guys, next we have Zeeman effect. First we will define Zeeman effect. The phenomenon of splitting of a spectral line into a number of lines in the presence of a number of lines in the presence of magnetic field is called Zeeman effect. Like if a spectral line is passed through a magnetic field, the magnetic field can either be a strong magnetic field or it can be a weak magnetic field. Then this spectral line is split into a number of component lines. This phenomenon is called Zeeman effect. First I will explain the experimental arrangement of Zeeman effect. So here we have the experimental arrangement of Zeeman effect. Now the apparatus looks like this. First I will draw the diagram and then I will explain each component. So here we have these are called pole pieces. And here we have source of light, and here we have the viewpoint. We have a source of light. This is the source of light. Let's say it's the sodium lamp, which is placed between two pole pieces. This is A, this is B. These are called pole pieces. This is pole piece A and this is pole piece B. And this sodium lamp is placed between these two pole pieces, which are represented by A and B. And they are made up of strong electromagnetics. They produce a strong magnetic field. Now the modified light, like light after splitting, once light pass through this magnetic field, it split into a number of components. So that is called modified light. This modified light can be observed by high resolving instrument. The instrument is either this one or it can be this one. And then analyzed by using a nickel prism. Why we use a nickel prism? Like here we use a nickel prism somewhere here or somewhere here. The purpose of the nickel prism is to check whether the light is polarized or not. So the prism is used just for the checking of the purpose that whether the light is polarized or not. Now this modified light or splitting light can either be observed, like the magnetic field direction is this one. Suppose this is the magnetic field direction. So we have 2 points for the observation point. One is this and one is this. So here if we observe the modified light, we are observing it in the direction of magnetic field, because the direction of magnetic field and the observation point, they are parallel to each other. So we call it view parallel to the magnetic field. And here we are observing the modified light in a direction. The direction of observation is this one, while the magnetic field direction is this one. So we are observing in a direction which is perpendicular to the field. View, this is the view perpendicular to the field direction. Now to observe light parallel to the field direction, like if we observe the light in a direction which is parallel to the field direction, a hole is drilled. Here we drill a hole. This is the hole into the pole pieces A and B. This hole drill, the purpose of this hole is to observe the modified light in a direction which is parallel to the magnetic field, while here we are observing the modified light in a direction which is perpendicular to the magnetic field. So based on this observation, there are 2 types of Zeeman effect. This is the experimental setup. There are 2 types of Zeeman effect. Now there are 2 types of Zeeman effect. There are 2 types of Zeeman effect. There are normal Zeeman effect and the second one is anomalous Zeeman effect. So first we will discuss normal Zeeman effect, number 1. When the modified light which is basically the spectral line, which is splitted spectral line, is observed parallel to the field. I means if we observe the splitted light, because we know that in Zeeman effect, a spectral line when passes through a magnetic field, it is split into a number of component lines. So if we observe those component lines in a direction parallel to the magnetic field, then each line or each spectral line is found to split into two components. This is called two components line. This is called normal Zeeman effect. Like if we observe the modified light or the splitted light in a direction which is parallel to the magnetic field, like if we observe through this highly resolving instrument, then each spectral line is found to split into two component lines. This is called normal Zeeman effect. So here, suppose we have a spectral line of zinc. Suppose we have a, let's suppose this is a spectral line of zinc, which is a single line without magnetic field, and B is 0. This is zinc singlet. Now, this component, this single component, let's suppose it is a frequency nu naught. Now, once we pass it through the magnetic field and observe it in a direction which is parallel to the magnetic field, then this single line is split into two lines. One with higher frequency and one with smaller frequency as compared to the frequency of unaffected light. Here we have B is not equal to 0, but in normal Zeeman effect we use a strong magnetic field. So this is called normal Zeeman effect. We pass a single spectral line. When there was no magnetic field, it looks like a single spectral line, but once it passed through a magnetic field, this single spectral line is split into two components line, one with frequency greater than this frequency and one with frequency smaller than this frequency. We can say that one component has higher frequency, this one, nu naught plus d nu, and the other component has lower frequency, this one, nu naught minus d nu, as compared to the frequency, this frequency of the original line. Now this original line is not observed in the presence of magnetic field. It's disappear. It's split into two lines. These two lines are different because their frequencies are different from this line. Though the original, once we pass this single line in the absence of magnetic field, then this line with frequency nu naught is unpolarized. If we pass it through the nickel prism, it is unpolarized. But on the other hand, the two components, like this component and this component, once they pass through the nickel prism, they are found to be circularly polarized. This is unpolarized, and these two lines are circularly polarized. These lines are called sigma line. Now, When we observe the same spectral line after passing through the magnetic field in a direction which is perpendicular to the magnetic field, like if we observe this spectral line by this high resolving instrument, spectroscope, then what will happen? This spectral line, which was initially, when there was no magnetic field, it looked like a single line. This is again the zinc singlet. When there was no magnetic field, it looked like that this spectral line is a single line, and it is unpolarized if we pass it through the nickel prism, and its frequency is nu naught. But if we observe this spectral line in a direction which is perpendicular to the magnetic field by using this instrument, then what will happen? This single spectral line appear to split into three spectral lines. It appeared to split in three spectral lines. So this spectral line is split into three spectral lines in the presence of strong B. Now the central component line is called, this is called pi component, while these two components are called sigma component. This central line has a frequency which is equal to the frequency of this unpolarized light or unaffected light when magnetic field was 0. And these two lines on either side of this nu naught, one is frequency which is greater than this frequency, and one is a frequency which is less than this frequency. So when the modified light is observed perpendicular to the magnetic field, then each spectral line is just found to split into three components. Each spectral line is found to split into three components. This central component is called pi component, and it is a frequency nu naught, which is equal to the frequency of the original light, original line. One of the two remaining component, like we have these two remaining component, this component has a frequency nu naught, nu plus nu naught, nu plus d nu, sorry, it's nu naught plus d nu, it's nu naught plus d nu. This is a frequency nu naught plus d nu, and this is a frequency nu naught minus d nu. So this component has a frequency, higher frequency nu naught plus d nu as compared to this one, and this one has a frequency, smaller frequency, lower frequency nu naught minus d nu as compared to this one. Now these components on either side of the pi component, they are called sigma component line. So this is what we call it normal Zeeman effect. Now the original line is unpolarized, while these three components, when we observe it in a direction which is perpendicular to a magnetic field, they are polarized, but they are plane polarized. Here they were circularly polarized, here they were plane polarized. So it means that the phenomena of splitting of a spectral line into three components line in the presence of strong magnetic field, three components when we observe it in a direction parallel to the magnetic field, and two components when we observe in a direction parallel to the magnetic field, then there are two components. If we observe in a direction perpendicular to the magnetic field, then there are three components. So it's either 3 or 2. 2 or 3 component line in the presence of strong magnetic field is called normal Zeeman effect. So I will stop my video here. In the next video I will discuss the anomalous Zeeman effect. Thank you.